somewhere in your parents' house or a secondhand shop, or the back of a shelf you have not looked at in years, there is probably a small gift book edition of Persian poetry, cloth-bound, gilt-edged, illustrated with cypress trees and wine cups. For about 60 years, from the 1880s through the First World War, it was one of the most popular books in the English-speaking world. It was quoted in speeches and stitched onto cushions. There were societies devoted to it. Soldiers carried it into the trenches. The poems are quatrains, short, self-contained, unillusioned. They observe that life is brief, that nobody knows what comes after, that the great kings are dust and their palaces are grazed by wild animals, and that in the meantime there is wine and bread, and someone to share them with, and that this is not a small thing, but very nearly the whole thing. They are beautiful and they are melancholy, and they have persuaded 100 years of readers that they know something about the man who wrote them. The man was a mathematician. It was his day job, and he was one of the best in the world at it. And there is a fair chance he did not write most of the poems. His name was Omar Khayyam, properly Umar al-Khayyami, the surname meaning tent maker, probably a family trade, and he was born in 1048 in Nishapur in northeastern Persia, in what is now Iran. He lived through the Seljuk Turkish ascendancy and worked under the patronage of the Sultan Malik Shah and his formidable vizier Nizam al-Mulk, which meant money, an observatory, and a mandate. The mandate was the calendar. Persia's was drifting against the seasons as calendars do, and Malik Shah wanted it fixed. Khayyam led the team that produced the reform of 1079, and the scheme they devised was superb. A pattern of intercalated leap years that track the solar year so tightly that the accumulated error runs to about a day in 5,000 years. For comparison, the Gregorian calendar you are using, introduced 500 years later, and still in service, drifts about a day in 3,000. The modern Iranian calendar is a direct descendant of his. So that is one achievement, a better calendar than ours in 1079. But it is not why he belongs in this book. Here is the problem he actually attacked, and to see why it mattered you need to remember where we left algebra. Al-Khwarizmi in Chapter 8 had cracked the quadratic, equations involving a square of the unknown. He gave complete procedures with geometric proofs for every case. That was the state of the art, and it stood. The next step up is the cubic. Equations involving the unknown multiplied by itself 3 times. And the cubic is not a small increment on the quadratic. It is a wall. Nobody had a general method for it. Not the Babylonians, not the Greeks, not the Indians, not Al-Khwarizmi. Particular cubics could be solved by luck or ingenuity. The general problem sat there unsolved for something like 2,500 years. Khayyam did not solve it either. What he did was extraordinary in a different way. He noticed that although you cannot corner a cubic with algebra, you might be able to catch it with curves. The Greeks had studied the conic sections, the family of curves you get by slicing a cone at different angles: the circle, the ellipse, the parabola, the hyperbola. Apollonius had written a monumental treatise about them, and to the Greeks they were objects of pure geometry, admired and thoroughly explored, and applied to almost nothing. Khayyam's insight was that each of these curves corresponds to a relationship between 2 quantities, and that if you choose your curves carefully and draw them on the same diagram, the point where they cross satisfies both relationships at once. Pick the right parabola and the right circle, superimpose them, and the horizontal distance from the origin to their intersection is exactly the number that solves your cubic. The curves do the algebra for you. You cannot compute the answer, but you can construct it and then measure it off the page. He worked this out systematically. Because he refused negative coefficients exactly as Al-Khwarizmi had, he was forced to break the cubic into a long list of separate types, each requiring its own pair of curves. And he went through them one by one and handled them all. It is the most sophisticated algebra written anywhere in the world at that date, and it would not be improved on for 450 years. And then he did something that I find more admirable than the mathematics. He wrote down what he had not achieved. He was perfectly clear that a geometric construction is not the same as an arithmetical solution, that he had found a way to produce the root without finding a formula for it. And he said explicitly that he hoped someone coming after him would succeed where he had failed. We have seen this before. Lu Hui in 3rd century China could not find the volume of the sphere, built the tool that would eventually crack it, admitted he could not finish, and left it for someone wiser. 200 years later, someone picked it up. Khayyam's message took longer to be answered, and it was answered in a place he could not have imagined, in 16th century Italy, in a public feud between two mathematicians competing for prize money, which will produce not only the formula he wanted, but a monster nobody wanted. That is chapter 11. He was right that it could be done. He was not right about what it would cost. There is one more thing on his record. He also wrote a commentary on the difficulties in Euclid, and went after the 5th postulate, the parallel postulate, the loose bolt from chapter 4. He worked with a particular four-sided figure, reasoning about what its angles must be if the postulate is denied, and derived a string of consequences. He did not succeed. The argument leans, somewhere in the middle, on an assumption that turns out to be the postulate in disguise, which is what happened to everybody. But hold the image of that quadrilateral, because it is the same figure Saccari would use in 1733, 600 years later, in the book called Euclid Freed of Every Flaw. The man who walked into non-Euclidean geometry, took careful notes, and refused to believe he was anywhere. So why is Khayyam a poet? Quatrains have been attributed to him for a very long time, and the attribution is genuinely uncertain. He was known in his own lifetime as a philosopher, astronomer, and mathematician. The title people used for him was one you would give a sage or a scientist, not a poet. The manuscripts assigning verses to him appear well after his death, and here is the pattern that makes scholars nervous. The number of poems attributed to him grows. Early sources credit him with a handful. Later ones credit him with hundreds. Later ones still with over 1,000. That is not what happens to a real body of work. That is what happens when a name becomes a category, when a certain kind of skeptical, wine-loving, mortality-haunted quatrain starts getting filed under Khayyam, because that is the shelf it belongs on. Some of the poems are probably his. Most, on the evidence, are probably not. Then, in 1859, an English gentleman scholar named Edward Fitzgerald published a slim volume of English versions. They are not translations in any strict sense. He selected, rearranged, merged, and rewrote, producing something that is at least as much his poem as anyone's. It sold nothing at all. Copies ended up in a remainder bin at a penny each, where they were found by Rossetti and Swinburne, who told everyone. And within 20 years it was a phenomenon. So here is the final accounting. Omar Khayyam is famous across the world for a book of poems that he did not entirely write, in a version by a Victorian Englishman who admitted he was making it up as he went, while the cubic equations that occupied his professional life are known to perhaps a few thousand people. And you have read this exact shape one chapter ago. Leonardo of Pisa, world famous for a throwaway puzzle about rabbits, under a surname invented 600 years after his death, while the Book of Squares, his real achievement, sat unread. 2 chapters, 2 of the finest mathematicians of the medieval world, both remembered vividly for the wrong thing. That is not a coincidence. It is a fact about how reputation works, and it is the doorway into the second half of this chapter. Now go south. Kerala is the strip of land along the southwestern coast of India, between the Western Ghats and the Arabian Sea, green, wet, thick with spice and rice and backwater. And for centuries one of the great trading coasts of the world. Romans came here for pepper. So did Arabs, Chinese, and eventually the Portuguese. Around 1340, in a place called Sangamagrama, a mathematician named Madhava was born, and he founded what is now called the Kerala School of Astronomy and Mathematics, a lineage of teachers and students that ran, remarkably, for more than 2 centuries. We know less about Madhava than we would like, because his own writings are mostly lost. What we have is his successors, who cite him by name over and over, attributing specific results to him with the care of people who are conscious of transmitting something important. It is a chain of scholars saying, this one is Madhava's. The motivation, as always, was the sky. Predicting eclipses and planetary positions requires accurate trigonometric tables, and accurate tables require some way of computing sines and cosines to many places. The Indian astronomical tradition had been building such tables for 1,000 years. Madhava wanted better ones. What he found in pursuit of better tables was this. Take an angle. Now take its tangent, the number you get from the ratio of the two shorter sides of a right triangle containing that angle. Madhava discovered that you can recover the angle from the tangent by an infinite sum. Take the tangent, subtract its cube divided by 3, add its fifth power divided by 5, subtract its seventh power divided by 7, and keep going forever. Alternating signs and running up the odd numbers. Every term is smaller than the last. The running total closes in on the true answer. Sum enough terms and you are as close as you like. That formula is known today as the Gregory series, after the Scottish mathematician James Gregory, who published it in 1671. Madhava had it around 1400. Now feed it a special value. If the two short sides of your triangle are equal, the tangent is 1 and the angle is 45 degrees, an eighth of a full turn. Put 1 into the formula and every power of 1 is just 1, so the whole thing collapses into something astonishingly clean. 1 minus a third plus a fifth minus a seventh plus a ninth forever, and the answer is 1/4 of pi. Stop and look at that. On the left, the simplest imaginable pattern. The odd numbers, flipped upside down, added and subtracted in turn. Nothing but whole numbers and alternating signs, a sequence a child could continue indefinitely. On the right, pi, the ratio at the heart of every circle, an irrational number with no pattern in its digits. The quantity that Archimedes cornered by grinding through 96-sided polygons, and that Zhu Shangji pinned to 7 places with counting rods and heroic labor. The two are the same thing. The circle is hiding inside the odd numbers. That result is called the Leibniz series, after Gottfried Leibniz, who found it in 1674. Madhava had it 270 years earlier. The Kerala school also derived infinite series for the sine and the cosine themselves, what a modern textbook calls the Taylor series for those functions, after an English mathematician of the 18th century. And they did something that demonstrates, better than the series themselves, how well they understood what they were holding. The pi series is beautiful and, as a practical tool, nearly useless. It converges so slowly that you would need hundreds of terms to nail down even 2 decimal places. They knew this. So they developed correction terms, extra pieces to bolt onto a truncated, some to jump most of the remaining distance. And with them, they computed pi to 11 decimal places. That is not somebody who stumbled onto a formula. That is somebody who understands the behavior of infinite series well enough to engineer with them. Their results were written up by their successors, and the great texts survive. The Tantra Sangraha of Nilakantha in 1501, and around 1530, the Yuktibhasa of Jyeshtha, written not in Sanskrit but in Malayalam, the local vernacular, and containing not just results but derivations, laid out step by step, explaining why they hold. So, did the Kerala school invent calculus? This is where I have to be careful, because there are 2 bad answers, and both are popular. The first bad answer is the old one, which is simply to leave them out, to teach the history of calculus as Newton and Leibniz, and their European predecessors, full stop, as if nothing happened in Kerala at all. That was the standard account in English for a long time, and it is indefensible. The results are there in dated manuscripts with derivations. The second bad answer is the triumphant reversal. Calculus was invented in India 3 centuries early, and Europe stole the credit. This is more satisfying, and it gets the facts of the first half right, and it still will not do. Here is the honest version, and it requires making a distinction that is worth having for its own sake. There is a difference between having a result and having a subject. Think back to Archimedes in Chapter 5. He sliced regions into many infinitely thin strips, and weighed them on an imaginary balance to find areas and volumes. That is integration. He got exact, correct answers to problems that would not be touched again for 19 centuries. And yet we do not say Archimedes invented calculus, and the reason is not chauvinism. It is that what he had was a superb technique for particular figures, the parabola, the sphere, the spiral, deployed one problem at a time, each requiring its own fresh ingenuity, and hedged about with an apology for not being legitimate. What Newton and Leibniz did was different in kind. They recognized that the two great problems, finding the slope of a curve at a point and finding the area under it, are inverse operations, two directions along the same road. They built a notation and a set of mechanical rules that let you differentiate or integrate an enormous range of expressions by following procedures without fresh genius each time. They turned a collection of hard-won individual results into an algorithm, and here the word from Chapter 8 earns its keep, that a competent student could be taught in a year. That is what inventing calculus means. Not the individual results, some of which were centuries old. The unification, the generality, and the machinery. The Kerala school has a real claim to more of this than Archimedes did. They had infinite series, they had results equivalent to integrating certain powers, they had a working grasp of limiting processes and convergence, and they had derivations. What they do not appear to have had as the general theory, the recognition of differentiation and integration as inverse operations, applied to functions in general, with a symbolic calculus for handling them. Their work was aimed at astronomy and stayed there. So the fair statement is this: they went further toward calculus than anyone before Newton, further than Archimedes, and much further than European mathematics had reached at the same date. They arrived at specific results that Europe would celebrate as major discoveries 2.5 centuries later. And they did not build the general subject. That is a large claim to make on their behalf. It has the advantage of being true. There is a further question, and it is genuinely open. The Portuguese arrived in Kerala in 1498. Jesuit missionaries followed, and they established themselves in Cochin and other coastal towns through the 16th century. Jesuits in this era were unusually well trained in mathematics and astronomy. They were actively interested in calendar reform and navigation. They learned local languages, they collected local knowledge, and they sent material home to Europe. Kerala's mathematicians were active in exactly those places at exactly that time. So the hypothesis has been put forward, seriously, by qualified historians, that Kerala results may have reached Europe through this channel, seeding work that later appeared under European names. The circumstances are suggestive. The means and opportunity are real. What is missing is evidence. No document has been found showing these particular results traveling. No European manuscripts citing an Indian source for them. No smoking gun in the Jesuit archives, which are extensive and have been searched. The mainstream position, therefore, is that transmission is unproven and that Gregory, Newton, and Leibniz most likely found their results independently. That position could change if a document turns up. It has not yet. I'm not going to pretend to resolve it. What I will say is that independent discovery is not a suspicious claim in mathematics. It is the normal one. We have watched it happen repeatedly in this book. Archimedes and Liu Hui, on opposite sides of the world, with no possible contact, both trapped the circle between polygons, and both edged up to the limit. Non-Euclidean geometry in Chapter 17 will be discovered 3 times in 15 years by 3 men who did not know of each other. The calculus itself was found twice, in England and Germany, within a decade, and the resulting priority war between Newton and Leibniz will get most of Chapter 14. Mathematics gets discovered more than once because it is there, and because when the surrounding conditions are right, the same questions become askable in more than one place at the same time. 2 independent discoveries are not a coincidence requiring an explanation. They are the ordinary weather of the subject. Which brings us to names and to the thing this chapter is really about. Consider the following list, assembled entirely from what we have covered so far. Gaussian elimination is in the 9 chapters, 18 centuries before Gauss. Cavalieri principle was stated by Zhu Zheng around 500 CE, 1100 years before Cavalieri. Pascal's triangle is in Yang Hui in 1261, who credits Jia Xian around 1050, 6 centuries before Pascal, and it is also in alchemy and in Indian combinatorics. Horner's method appears in Shinjiosho in 1247, nearly 600 years before Horner. The Gregory series and the Leibniz series were both Madhavas. Arabic numerals are Indian. And Pell's equation, which we have not discussed, was studied by Brahmagupta and solved by Bhaskara, while John Pell had essentially nothing to do with it. Euler misattributed it and the name stuck. There is a name for this. The statistician Stephen Stigler proposed what he called Stigler's law of eponymy. No scientific discovery is named after its original discoverer. And in the paper where he proposed it, he noted, with obvious pleasure, that the law had already been discovered by the sociologist Robert Merton, so that his own law was an instance of itself. Why does this happen so relentlessly? Part of it is straightforwardly ugly. 19th and early 20th century European historians of mathematics often wrote as though the subject ran from Greece to the Renaissance, with a 1,000-year nap in between. And the material we have spent part 2 on was either unknown to them or dismissed. Some of it was not translated. Some of it was translated and ignored. That is a real failure, and it deserves to be named. But most of the mechanism is more mundane, and understanding it matters more than being angry about it. A result gets a name when it enters continuous use, when it is picked up, built on, taught, cited, and made load-bearing in an ongoing tradition. The name attaches to the point where it entered the stream that leads to us, which is not always the point where it was first found. Zhu Jing's principle was correct and beautiful, and then sat in Chinese texts that European mathematicians could not read, and Chinese mathematicians largely stopped developing. Cavalieri version fed directly into Italian and then European analysis, and from there into calculus, and from there into everything. He is not more deserving. He is more connected. There is a lesson buried in that which I think is genuinely important, and it is not the one about credit. Discovery is not enough. A result that nobody picks up does not do anything. It sits in a manuscript, correct and inert, waiting for a reader who does not come. Madhava's series were right for 270 years before Leibniz found them again, and during those 270 years, they changed nothing outside Kerala. Not because they were less true, but because the network that would have carried them did not exist. Mathematics is not just a body of facts. It is a conversation, and a discovery that never enters the conversation might as well not have happened, however brilliant the person who made it. This is why the transmission question in this chapter is more than an argument about credit. If Kerala mathematics did reach Europe, then the conversation was one conversation, and we have been telling its history wrong. If it did not, then 2 separate conversations found the same truths, and the tragedy is not that anyone stole anything. It is that the 2 never met. That is the end of part 2. Look at what has arrived in 900 years. Negative numbers, calm and unremarkable on a Chinese counting board. 0, promoted from a gap in the table to a citizen of arithmetic, with rules for its behavior and a wall built where division by it would have been. A decimal place value notation that could express any quantity with 10 signs. Algebra, the audacity of naming what you do not know and calculating with it anyway, made into a systematic subject with procedures and proofs. The word algorithm, cubics, cornered by intersecting curves. Infinite series, summed and corrected and pushed to 11 decimal places. And a body of practical arithmetic strong enough to run a banking system across a continent. Almost none of it happened in Europe. All of it ended up there. By 1500, the whole inheritance had been assembled in Italy, in Latin and vernacular translations, in printed books, taught in commercial schools to boys who would become bankers. Europe had every tool that Babylon, China, India, and Baghdad had produced, all in one place, at one time, for the first time in history, and, crucially, a printing press to spread whatever happened next within months rather than centuries. What happened next was that somebody finally answered Omar Khayyam. In the 1500s, in the university towns of northern Italy, mathematicians began solving cubic equations, algebraically, really solving them with a formula. They did it in secret because in that world a method was a weapon. You kept it hidden, challenged a rival to a public contest of problems, and destroyed him in front of an audience for money and a chair. The story that follows involves a broken oath, a bitter public feud, a book that should never have been published, and one of the great scoundrels of the Renaissance. And out of it, unbidden and unwelcome, came the next monster. Because the formula that solves the cubic sometimes demands, in the middle of an otherwise ordinary calculation, that you take the square root of a negative number, an operation that is not difficult but impossible, since no number multiplied by itself gives less than nothing. The mathematicians who found it thought it was garbage. They held their noses and carried it through the arithmetic anyway, and discovered that it obligingly canceled itself out and left the right answer sitting there. Descartes, 3 generations later, would give the thing a name meant as an insult. He called it imaginary,